Today is first lecture on basic electronics. We will study about it is general overview of the basics of electronics, where we start with the semiconductor, what is semiconductor, and PN junction, diode behavior, and transistor. Then we will go to how we can make a device out of it, and then finally on the digital communication part. So this all these electronic devices is a semiconductor. So, and what's special about the semiconductor? We can characterize material into uh, metal, insulator, or in somewhere in between semiconductor. Right? they they can be characterized whether material will be metal, semiconductor, or insulator, depending upon its resistivity, conductivity, or we can also say the resistivity. For example, for metal, uh, around 10 to the power minus 2 to 10 to the power minus 8 ohm meter. While for insulator, these value are in the range of 10 to the power 11 to around 10 to the power 90. And somewhere in between is, is 10 to the power minus 5 to 10 to the power 6 ohm. If you see the range wise, the semiconductor has the wide scale where its conductive resistivity or in terms of the conductivity can be varied. This is one of the important thing, and because we can change actually its conductivity of a semiconductor. Same semiconductor, for example, if metal is copper, so it has certain conductivity, it's fixed value. And for the semiconductor, although it is same semiconductor, but we can change its conductivity. We change it, we do it by adding an external element that we will discuss later. And also optically, we characterize also this material based on the energy band gap. The band gap is the energy gap between the conduction band and the valence band. Like for example, it is PB is conduction band and WB is valence band. And this is around uh, greater than 3 electron volt for EG for insulator. And for semiconductor, valence band and conduction band, it is less than 3 electron volt. While for the case of metal, they actually overlap. Semiconductor, this is for metal, where the conduction band and valence band overlap, right? And it because silicon is bonded by a covalent bond. It has valency of 4. So if I make silicon, now this is a let's consider this is a typical silicon structure where each atom has bonded with the other four atoms through a covalent bond. Yes, this side also has electron and this side also has electron, right? So this is when this is at 0 Kelvin, if T equal to 0 Kelvin. So there is no bond breakage or anything. They are fixed. Everything is perfect. So in this case, there is no electron available in the material for to conduct the charge carry current or conduct conductivity. So in that case, it acts as good as insulator. But however, what we do if we heat a sample provide heat our sample or we rise the temperature, then it will receive its energy. Then this covalent bond they break. So what will happen when on gaining this energy? So this bond is break and this bond is break. Then is now this electron is still here, and this electron is now free. It break the bond and now it's free, leaving behind a empty space. This is called hole, or we represent it as plus as positive charge. So what has happened when we increase the temperature? This bond is broken. Uh, so what has happened when we increase the temperature? This bond has been broken. That has resulted into a generation of electron as well as hole. So basically at T greater than 0 Kelvin, basically about room temperature, of course, when it is not there, there is some precarious bond that has result into the presence of charge carrier. Now this material silicon have some conductivity. Now we represent N for electrons, number of electrons, and P for holes. So in that case, equal number of electron and holes will be generated, N and P, and we will say its concentration is Ni, which we call intrinsic carrier concentration. Okay, this is Ni is usually Ni is typically around 10 to the power 10 per centimeter cube. This is a typically concentration of value of a intrinsic carrier concentration for silicon. So when there is a absolute zero, there is no charge carrier present. But as the temperature increases, some of the covalent bond will break. This will lead to generation of creation of the electrons and holes. And this intrinsic charge carrier concentration around 10 to the power 10 per centimeter square. Right? Now, this means we can change the material conductivity by temperature, but this is not what we want. We want, okay, at room temperature, we want greater charge carrier concentration. By the way, this value is for the typical room temperature, which is around 300 Kelvin or around 27 degrees Celsius. But how about if you want more than that? So this we can do by doping our silicon with a external element, and they are called doped semiconductor. Doped semiconductor, right? Suppose if we doped our semiconductor with a pentavalent atom such as phosphorus. So let's see what will happen. We have a silicon. Again, I will throw silicon. This time I have phosphorus in between, and phosphorus has 5 electrons. Outer shell. So what you will do? 4 will consume in this bonding. There will be an extra electron which is available. So this, by doping phosphorus into silicon, we are getting an excess of electron, right? Suppose we doped this material with Nd for the doping concentration, and we will get a charge carrier, N, which is basically electron charge carrier around. If we suppose if we dop with a 10 to the power 16 atom or 17 atom, this is will be the charge carrier concentration that will be available in a semiconductor, and this type of material is called N type semiconductor when we dop with a pentavalent, right? But as I mentioned, these are at the room temperature, so it's mean there will be also presence of holes, and of course they will be in less in number. So there is the concept of majority charge carrier and minority. So for n-type semiconductor, the charge carrier that are generated is actually the how much we have actually doped this phosphorus concentration, and this will be called n. And since this material is n, so we will denote it as n with a subscript n. So n on n side. So basically number of electron in n-type material. And of course, since this is antimatter, so they will be majority. But there at the same time, there will be some minority charge carrier which are holes which are thermally generated. And we know the holes are represented as P, small p. And since they are on n side, so they are represented as P on n side. So they are majority charge carrier, they are minority charge carrier, and their majority charge carrier is somewhere around equal to ND, that the number of dopant atom of phosphorus that we have doped in our silicon. Similarly, if we dope our material with the trivalent, like for example boron or aluminium, then you will also get NK charge carrier concentration, but this time it will be of holes. Right, so it has 3 electrons, so these will be bonding, but there is one missing. There has to be 1 electron, but there is no electron. So this is basically what is it? Hole. Presence of hole. So because there was missing 1 electron missing, which has generated into the presence of holes, and this hole actually move around. What happens sometimes, like since it is a random process, the electron that are present here, it will come on this place, and this will go into this place. So it is equivalent to the movement of holes. The electricity move in the opposite direction of electrons. So it's look like okay, now this will come on this side, and this will be filled, and this will have now come at this side. So it is actually movement of holes. So for in that case, this type of material is called P type, and number of charge carrier concentration is called acceptor type. This time that time earlier it was ND, now it is Na. So it will generate number of holes P, and it will be on majority side, so P on P side. Similarly, and similarly there will be minority charge carrier which will be electrons. So and on P side, this will be majority, and this will be minority. Okay, and again there is also a relationship that n on n side and P on n side is actually always equal to Ni square. These are the relation that may be useful when you do it later. Or also the P on P side or N on P side is also Ni square. This is also called mass action law. Okay, now so until now we see okay, semiconductor has a property that we can change its charge carrier concentration and internal conductivity. How it will conduct electricity by changing, but it's also affected by temperature. But we can also dope either pentavalent or trivalent, and we can change its charge carrier concentration. We can make either electron rich or hole rich. Basically, majority charge carrier could be electron or holes, depending on we call it N type and P type. And they are number of an atom that we are doping it. We will call it charge carrier concentration. Okay, and also this this P on P side is positive, so acceptor ion they are of by themselves they will be negatively charged. Similarly, this Nd since they are generating electron, they by themselves will be positively charged. This will be useful later. Now move forward uh, in this way. Now see, let's go for the current. Now we have electrons. First, we'll see. electrons and we have holes, right? So if there is electric field, something like this, then electron will move in the in opposite of electric field, and holes will move in the direction of electric field, right? And we know that these both are present in the semiconductor. Whether which one is in higher in concentration, that's a different question, but they are there. But at the same time, if we know if there is some concentration gradient, some part of the something has a higher concentration of particular species, then it will diffuse to the lower concentration value. This is called diffusion, right? Presentation. This is some cube, some imaginary cube, right? And this side has lots of free electrons. So, and this of course has no electron this side, so they will try to move because there is a concentration gradient. So, and whenever there is a movement of charge, that has led us to the flow of current, right? So the current that we have basically two component or two types or two mechanisms follows. One is drift, which is when because of this electric field, and one is diffusion. Diffusion is when there is a due to concentration gradient. And for a semiconductor, usually current density is equal to conductivity and electric field. Can be and this charge concentration can also be written as Q, charge carrier, and mobility, and presence of number of charge carrier. Whether it's for electron, it will be mu n, and for a hole, it will be p. And similarly, diffusion, because of the this will be the drift, and for diffusion it will be proportional to basically Q P of n. This is a diffusion coefficient and the concentration gradient. This is for electrons. Similarly, it will be minus Q diffusion coefficient for holes. So basically, what I'm trying to convey, there is a presence of electron and hole, and there is electric field. Then they will move. This will result in one type of current, which we will call drift current. And if there is a concentration gradient of this electron or hole from one particular place to other places, there will be concentration gradient, and because of it they will move, and this will lead to a current. We will call it a diffusion current. Right, now let's move forward. We have mentioned there is a p-type material and there was also n-type material. Let's see what happened. What are they? Let's say this is p-type material. So it p-type material is docked with a acceptor type, and acceptor type has negative charge. So these are immobile ions. There are lots of them, right? So correspondingly, there will be how much there will be this acceptor. There will be number of holes, equal numbers of at least equal number of holes will be there. Of course, here and there will be some electrons will also be there, which are minority charge carrier. And these they are fixed. They do this ion are fixed. They are fixed with the Indian lattice. They do not move. It's only the charge carrier that move. Similarly, we have n-type material. This type it has random distributed everywhere ions. So it will have electrons, equal number of electron at least in majority charge carrier, and here and there will be some holes. Right, now let's see what's happened when we bring them in contact, p-type and n-type material. So let's say this is the boundary. So, Let's say this is the boundary, this is p-type material, and this is n-type material. Now for symmetry, what I am doing, so this side will have holes, right? They were in majority. This side has electron in majority. So what they will do, electron will try from this side, it will try to go this side, right? This goes to the direction. Electron will try to go on this direction because they are more in number here. So what will do, they will leave behind ions, uncovered ions. So they will be negative. Similarly, electron leave from n type and go to p side, leave behind this immobile ion. Now, I'll just so this has the electron holes. Now they move from this side to this side, and this movement has led to the diffusion component of the coin. And you see there are now immobile ions, positive side or negative side, so there will be an electric field, right? So if you see the direction of electric field, since as I mentioned, the holes go in the same direction, so they will oppose this movement of the holes that were earlier going because of that concentration gradient. They oppose. Similarly, the for a movement of electron, this electric field oppose. So in that way, they are equilibrium, and this field, so it is opposing. So after some time, they will no longer a movement, and this is equilibrium condition. So there will be a semiconductor at the junction. There will be an immobile ions. There is no charge carrier. So only these ions are there, and there is a built-in electricity. These are called built-in electric field, right? Now again, these were all for the majority charge carrier. Now there are also some minority charge carrier electrons for their p type, right? And if you see the electric field direction, they will favor the movement. So this electron will simply go. And similarly, the holes on this side will go in this direction. But they are in minority. At equilibrium, diffusion and drift component, they are almost equal, but in opposite direction. So at equilibrium, there is no flow of charge carrier or something. So this is one case, right? Now, now what's happened? This is called PN junction. This is the basic of a PN junction diode. Now what's happened? And also before that, I will also draw a separately for band diagram. This is conduction band, and this is valence band, and material is P. Similarly, this is conduction band, this is valence band, and material is N type. Since in this they have majority of charge carrier of holes are majority charge carrier. So the Fermi level, which we will have later, E energy level, they are close to the valence band as of now. Not moving out, but just understand for the p-type material there is a Fermi level with energy EF, they are close to the valence band. Similarly, for conduction band, they are close to the valence band. This is when they are not in contact, right? Now, what's happened when they are made in contact? What happened is that they actually aligned their Fermi level throughout this from p side to n side will be the same. What does that mean? For alignment, we have to shift this downside and this we will go upside. So how it will look like? Something like they will bend. And this is p side, this is n side, and that is the equilibrium. This is Fermi level, and this the electron that are there on this side, they will face a barrier, which is of this side, potential barrier, in which are because of that this built-in potential that field at the junction that are the opposing this flow. Right. Similarly for the holes. So what's happened? We can change this field or this potential if we apply a potential. Let's say we made a connection such that we make this connection p side with a positive and we connect n side with a negative. So p side is positive, so it's positive, so it will repel electron. So what we will have, it will push more, it will push more holes towards the n side material. N side. So what does that mean? That it increases the diffusion component. Earlier there was equilibrium. Now there is no longer equilibrium. When we apply this potential P, we have it act as a opposite to this internal field, and this will allow more holes to reach to the other side. Right? In this way, we will see a current in the forward direction. And this is because when this is equilibrium and we apply a forward bias, what's happened is actually this barrier has actually reduced. This has reduced. This was a V naught. Now it is V naught minus whatever the potential that we have applied. So this has reduced, which has led to the crossing of electron from n side to p side, and then we get a current. Now see what's happened if we connect in a opposite direction. I'm drawing here again. So this is p side, n type, and this region actually is called depletion. Was the case when we apply a forward bias. What was happening when I told there was an electric field there, because of which now this effective width of depletion will actually reduce this. Electric component is actually reduced, right? And we see a flow of current. Now what's happened, this is when this side was connected with the positive terminal, this side is with the positive. Now what's happened if we connect the negative terminal? Then this depletion rate is negative, so it will attract electrons, so they will more uncover. So when we this the depletion rate only increases. Now what will happen? Uh, this there will be it is as good as this much. Like there is no actually flow of majority charge carrier holes in this side, but electron that was there, they will again go this side, and this side, the hole that are present will flow this side. So there is actually a flow of current for saturation of minority charge carrier. Minority charge carrier. In the forward wire, there was also current for this, let's say for forward wire, and they are due to majority charge carrier. So overall, we have beta semiconductor, we have n-type semiconductor, and when we combine them, they're actually at the junction. There is a formation of depletion rate, which consists of immobile positive and negative ions that we use for the doping. Now, because of when we apply a forward bias, uh, this barrier actually reduces, and we see injection of holes from p side to n side and electron from n side to p side that has resulted in one current, majority charge carrier current, but at the same time there is some minority charge carrier current, which is opposite to this one, which is the electric component, and they are simply very small. These majority charge carriers current, because of this they are very small, because majority charge carrier of course very high. Now if we plot this graphically, this is like, and this is how when we go or sometimes start to increase. And of course at the back side there is also this is very, and remember this scale is very different. This is milliampere scale and this is nanoampere. This is forward bias and this is reverse bias. This side, right? And basically this current, if we try to compare, this is current is by s to the power by n. This is a diode current equation in PN junction, the current that is flowing. Now let's say when we apply now potential V equal to 0, that's the equilibrium case. In that case, how it will be? I will be Is e to the power 0 minus 1. So basically Is 1 minus 1. So I equal to 0. So when there is no bias, there is no actually flow of current. Now what happens, like if, um, if V is positive. So what's happened? So the current will be I equal to IS x to the power UV by minus 1. And basically this thing, if I write it, potential, now this proportion will be very big because it is an exponential function as compared to this system. So in forward bias, we can say the current is actually as good as because of I equal to IS e to the power UV by. So what's happened when we increase the potential? First it is slow. After for the silicon case, after let's say around 5.5 volt, it start to increase and so then by actually when it is like 8, it has actually 0.8 has increased substantially. If you draw a line on an angle, we say this 0.7. This is also called this is typically built-in potential value. This is typically value for a potential at the uh, potential at the diode. Built-in potential at the this is actually typically value of potential beyond which it start to flow a current uh, in a large amount. And when and of course, what's happened to this when we apply a negative bias, when we use negative. So similarly, so will be I equal to IS potential minus UV by KT minus IS. So this will be very small. So I is as good as IS just in the positive direction. So this is how a diode should behave. But what's happened if we apply too much of a potential? This try we suddenly start to increase very sharply. This is called breakdown. This is called breakdown potential. Now, what's happened? What's happening is here. There's a mechanism you can understand from this. What's happened when you apply more and more and more potential in reverse direction, this direction, the field inside this material is increasing. So what's happened? Of course, there are iron, but there are also silicon. So it breaks the silicon atom covalent bond. So what in the very first point where I show the thermal generation of charge carrier. So it breaks the bond of silicon atom covalent bond, generating electron and holes. And this electron and holes will move in as per the direction of electric field, and suddenly there is an increase in sharp increase in current. So this breakdown voltage is called breakdown voltage, called Zener breakdown. Now, suppose what happened, this depletion width is very large. Suppose in the we have a case, the depletion width is very large. So what's happened is that these electrons that are being generated here, they will get sufficient kinetic energy, and they will strike the other bonded silicon, and in turn generate more electron holes here. So it's like impact ionization. So it's like moving very fast because it was an electric field scattered with the atom, ionize it, in result generate also electron and hole. And this way we see an avalanche. And this is voltage. Usually this is called avalanche breakdown voltage. Happen usually at the higher voltage. And what's the difference? Difference between Zener breakdown and avalanche breakdown is that in Zener, depletion width is not very thick. There is impact ionization happening. Field is high, so breaking the silicon bond, generating electron and hole pair. And they are, because of this field, they are moving across. And we select them, we create sharp Zener current. So it's called Zener breakdown. In case of avalanche, depletion width is big, so they, because of this electric field, the bond broken electron, they will move and they gain sufficient kinetic energy and they get scattered with the atoms of silicon and in turn generate more charge carrier in between and we get a sharp impingement. It's called avalanche. Usually for the Zener breakdown to happen, the depletion widths are usually made smaller. For avalanche, this should be thicker. This we can control by doping large charge carrier concentration, large dopant. Higher the dopant, the depletion width is actually smaller. When I say smaller, but the thickness smaller is because, for example, if you have a big bucket and you want to take only 5 ml, so the change in the surface level will be very small. So if you have only one bottle and you take a 5 ml, the change from the top will be higher. So this could be, you can understand the effect of doping level on the this depletion. So that's it for today's lecture. I will continue more in the next.